first chapter is really an introduction where I want to provide a philosophical sense of STEM education that we embrace so you understand where this program comes from. And the best way to say that is that we believe all of formal education, all classroom-based education, from the time students come in at the pre-K side of the pipeline until they graduate and exit the pipeline, all of formal education has one core goal. And it's a recognition that at some point you're going to graduate. Maybe it's high school, maybe it's, in your case, an undergraduate institution with an undergraduate degree. We hope many of you go on to graduate school, but you're going to get a diploma and a handshake. And what that handshake is going to say is, congratulations, you're now on your own in the real world where you're going to spend your professional careers. Which means that all of formal education is about preparing our students for the real world. And in STEM education, if we want to inspire some of our students to want to be scientists and engineers, professional researchers, it's critically important while they're in class now that they understand what is expected of professional scientists and engineers in the real world, so you all can make informed decisions about whether or not you want to go into a STEM career. And if that's the case, we feel the best way to allow students to understand what is expected of professional researchers is to allow the students to be professional researchers right now by taking a real world experience, hopefully from the frontier, putting it in a classroom environment or a formal education environment, and students get to experience for themselves what scientists and engineers get paid to do. How do you all feel about what I just said so far? Is everybody on the same page? Okay, cool. Now there's one caveat to that. And so if you go to one of your professor's offices, you'll see a computer on her or his desk. If they're experimentalists, you're going to go down to their laboratory. You're going to see expensive laboratory equipment. They're going to need to go to conferences to present. They might need access to a supercomputer or a super collider or a big telescope. And all those together are what we call research assets. And the way that research assets are secured by researchers in the United States is typically a federal agency like NASA or the National Science Foundation have a precious and limited research asset, typically grant money, in a certain discipline, never enough to go around to all researchers that want it. So the way that that federal agency gets the asset out in an equitable way is they issue a national call for proposals. And research teams all over the country in absolute secrecy design a research program around the use of that asset, and they write a formal proposal against what's called a proposal guide to make the case for why their team ought to get that asset as opposed to all these other teams. And everybody knows that the competition is pretty stiff because everybody and their grandmother is putting in proposals against these limited announcements of opportunity. And if the federal agency is NASA, what NASA will do is we'll take all the proposals coming in and convene a review panel. And the review panel will strictly grade all of the proposals against what's called a proposal evaluation rubric, which is embedded in the proposal guide. And only the teams with the highest of grades get an award letter, and the vast majority of teams get absolutely nothing. And it doesn't matter how hard they how hard they worked on that proposal. So here's how it connects to STEM education. If we want our students to understand what scientists and engineers have to do in the professional world, and we bring a real world experience into an undergraduate institution like yours, well, once you get that handshake and the institution says, congratulations, you're on your own in the real world, if only then does the former student say, I didn't know scientists and engineers have to compete. Nobody told me that. And I didn't know scientists and engineers have to be absolutely superb technical writers, writing proposals with embedded citations in the text and a bibliography, and they have to write papers on their research results. I didn't know I had to be a superb technical writer. And if that's when they find out, we in formal education have failed them because they're not ready for the real world of STEM. And so SSEP tries to capture that authentic experience as well as a research proposal competition. So students get to see that, yes, we have to compete for resources. That's how it's actually done in the real world. And we have to write proposals, and we have to go through a formal proposal review process. So does everybody understand that larger landscape of what we're talking about? And let me say one other aspect of this that I think is critically important, and that is, if you ask scientists and engineers, what do you get paid to do? They're going to tell you we're in the business of opening ourselves up to innate curiosity and asking questions. We are in the business of getting paid to ask questions. In education, we say that's inquiry-based learning. And scientists will also tell you, and once we ask a question, it defines a problem to be solved. So we have to frame a pathway to an answer, which typically could be an experiment of some sort. And the idea then is to answer the question, you have to poke your world. You've got to poke your universe. You've got to get data and evidence to come in. And you then interpret that data and evidence to understand how the world works, and more specifically, address the original question you asked to see if you answered it. In education circles, we call that evidence-based learning. So scientists and engineers get paid to do inquiry-based, evidence-based learning, which is process learning, as opposed to content learning. It's not about shoving a fire hose of content at someone's head and asking them to memorize everything. That's not learning. That's antithetical to what is expected in the real world. In the real world, learning is about inquiry-based, evidence-based, process-based learning, and content goes along for the ride. And what I think is also important to say here is that if you, when our children are first capable of expressing themselves, that's when the unending stream of questions begins. You can ask your parents, do you remember the time when I started asking questions? And they're going to smile and they say, yeah. And you started asking lots and lots of questions. We are born curious. We're born to explore. We're born to ask questions. We are born inquiry-based learners. And if you're a parent and you remember the time when your infants were testing their world by exploring near versus far and up versus down and color and texture, they were poking their world. And in response, the world around them gave them data and evidence to interpret. So these young humans have the ability to understand how the world works and navigate through it successfully. We are born evidence-based learners. Humans are born to do inquiry-based, evidence-based learning. In science, we call that the scientific method, but that's a misnomer. It has nothing to do with science. It's discipline independent. And in STEM, if you take a real experience from the frontier, which requires inquiry-based, evidence-based learning like researchers do, and you put it in a classroom and you ask students, here, do this, it should feel natural because you're born to do that. Does everybody understand what I just said in terms of that philosophy of approach? Okay. And if you ask, what are the skill sets associated with inquiry-based, evidence-based learning? Well, it starts with ownership in learning. You have to look around your world and be curious. You have to ask the original question to start a personal journey or define a problem to be solved. You own the learning experience. That's where it starts. And then now to solve the problem, you have to critically think and problem solve. You have to navigate an interdisciplinary landscape in order to secure the core knowledge necessary to solve the problem at hand. Typically, we work in teams, so that's really important. And the reason that teams are important, one core reason, is that when you express your thoughts and ideas to others, orally or through the written word, so communication skills are important, you end up with team think, which means that you come up with ideas that are bigger than just you. So all of those are skill sets associated with research on the frontier, and that's what scientists and engineers exercise every day in their jobs. Everybody with me on that? Okay. Does anybody have any comments or questions with regard to that? Okay, so that's the education philosophy of approach. And now we're going to go to chapter 2. So I'm going to pause and now I'm starting over again. So now the next part of this is, how does the student space flight experiments program work? How does it capitalize on that philosophy of approach? Well, we wanted to create an authentic research experience that was absolutely authentic. It could not be a simulation. It needed to be inspirational. It needed to be in our area of expertise. So, what we would give each of your institutions is your own space program. And what we would give to UCF and what we would give to St. Petersburg College is a single flight slot. Each institution gets one flight slot to fly one student team designed experiment to the International Space Station and have the astronauts operate it simply as your technicians according to your student flight team's protocol. So UCF is going to have an experiment on station. St. Petersburg College is going to have an experiment on station. But after you come up to speed on the microgravity curriculum, and I'll tell you a little bit more about that in a couple of minutes, you're going to break into teams. And what UCF and St. Petersburg College are going to do independently, since they're like NASA, each of your institutions has a precious and limited research asset, not enough to go around to all of your student teams that want it, because only one student team from each institution is going to be selected for flight. So each institution is like NASA, and you issue a local call for proposals. And all of the research teams at UCF each team is going to design a science experiment, and the same is happening for the teams at St. Petersburg College. And let me explain how the STEM comes together in an authentic, seamless way, okay? Each team is going to design a science experiment in a science discipline of your choice. But the science experiment design is going to be constrained by the engineering imposed by the flight certified mini laboratory that must be used. Easy to use mini lab, but you must use it. So its engineering constraints constrain the design of the science experiment. And the design of the science experiment is going to be constrained by the technology of flight operations to and from low Earth orbit. And the experiments are going to be characterized in terms of data analysis. So they're going to be characterized through the language of nature, which we call mathematics. So that's how you get science, technology, engineering, and math. And just to give you a real world example, and I know faculty on this on this Zoom can give real world examples from their areas of expertise too. But my PhD is in astrophysics. My specialty is planetary atmospheres in our solar system beyond Earth. And let's say I want to measure the composition of the atmosphere of Mars using a major telescope on the big island of Hawaii. And I want to use the spectrometer that is made available by the telescope to the research community. So I want to use this instrument to measure the composition of the atmosphere of Mars. The first thing I have to do is get the operating manual for the spectrometer. That provides the engineering constraints and the technology constraints imposed by the use of this instrument on my experiment, on my science. In other words, the operating manual tells me what the spectrometer can do and what it cannot do. And only once I know those constraints can I design a science experiment that the spectrometer can deliver on, because what's the point of writing a proposal to the telescope time allocation committee if the proposed science cannot be done by the spectrometer? So does everybody understand how engineering and technology limit the science? That's how SSEP works. You have to design a science experiment, but only after you read backwards and forwards the mini laboratory operations page, which has all of the engineering and technology constraints on experiment design. So everybody with me on that? Give me a thumbs up if that sounds good. And by the way, has UCF joined us yet? With video, I don't see anything, so it sounds like you're hearing me, but that would be it would be nice to confirm that you're still hearing me. I don't know. Okay. Tim, do you see anything on chat, by the way, from them recently?
It doesn't look like there's anything on chat.
Okay, all right. So everybody understands how we get STEM. And so what then happens is each of your institutions, all of the teams in your institution will write a formal proposal against a real proposal guide to make the case for why that team ought to get your flight slot. And then your proposals will go to your faculty, and they will set up a step one review board of faculty. And using the proposal evaluation rubric, they will strictly grade all of the proposals coming in and select three finalist proposals from each institution and send them to us. We then convene the step two national review board, likely at NASA's Goddard Space Flight Center, and they will select the flight experiment for UCF from your three finalists, and they will select the flight experiment for St. Petersburg College from your three finalists. And now you've got the flight teams moving forward. Everybody understand how that works? Now, you might think this is kind of weird, but when we were designing this program, we didn't really care much about the flight experiment. Sure, that's the carrot, right? It's like you are proposing to get a flight slot to fly an experiment on the International Space Station operated by the astronauts. That's like way cool. But from the program design vantage point, our objective in STEM education was to immerse a local community of students in real science experiment design that they own, constrained by real world engineering and technology constraints, write real proposals against a real proposal guide, and go through a formal proposal review process. And that is accomplished at both of your institutions. Everybody with me on that? Does that make sense? Okay, so now your flight team moves forward with 2 months to optimize their experiment before we have to lock in the list of fluids and solids that comprise that experiment. That list is then sent to NASA Johnson Space Center to the Office of Toxicology for 4 months of flight safety review. And after flight safety review, 2 to 3 weeks before launch, your flight team will fill and seal their ground control and flight mini laboratories and ship the flight mini lab to Houston for payload integration. Rhodium, the payload services provider, will take your experiment and put it into all of the experiments for Mission 21 and put it into a single SSEP payload, hand it over to NASA. NASA will carry your experiment to Kennedy Space Center and hand it over to SpaceX. SpaceX will put your two experiments into a SpaceX Cargo Dragon on top of a Falcon 9 rocket, and it will launch from Kennedy Space Center from historic pad 39A, the same pad from which all of the Apollo missions to the moon launched and over 100 space shuttle flights. Your experiment will be carried 250 miles above the surface of the Earth and accelerated to 18,000 miles an hour, which means it will be moving 4.5 miles every second. It will be brought aboard the International Space Station, the largest spacecraft ever constructed, which is larger than a football field. And the astronauts will operate the experiments for 4 to 6 weeks on orbit. After that period is over, the experiments will be put back into Dragon for a deorbit burn. The vehicle will likely splash down off of the east coast of Florida. A recovery ship will pick it up. The payloads will be pulled. The SSEP payload will be deintegrated and all the mini labs will be inspected and then shipped overnight back to the student flight teams for harvesting and analysis. You can send a delegation down to the launch to watch the bird fly, and you can send a delegation to the SSEP Very Real Authentic Research Conference at Kennedy Space Center, because we felt immersing student delegations in a real research conference should be part of an authentic STEM experience. And then the last piece of SSEP is that ever since human spaceflight began, a NASA astronaut crew would work with a NASA artist to create a graphic design that captured the mission objectives. And that's what's turned into that cloth mission patch that they wear on their flight suits. And it's also the graphics that brands all of the mission documentation. So we'll actually fly up to 2 mission patches with your flight experiment. And undergraduate institutions typically reach out to local area school districts, pre-college students, so that you can reach out through the central office to art and design teachers, and you can get hundreds to thousands of students engaged in the mission patch art and design competitions, which builds program-wide awareness for your participation in SSEP, but more importantly, it allows your institution to reach out locally to the community in a powerful way. And so this is actually an authentic STEAM initiative where A is inserted for art. So does everybody understand how the Student Spaceflight Experiments program works? Give me a thumbs up if you do. Does everybody understand how it grows organically from that philosophy of approach, that authentic philosophy of approach? Do we have any comments or questions before we move on to the next section?
Not to interrupt Dr. Goldstein, but I did want to mention that it looks like the other campus is hearing you and also on video. So
Great, wonderful. All right, that's good to know. So how are we doing so far? Cool?
great.
Okay, so now let's pause this. And I'm going to tell you, we're going to get to some more challenging chapters in a couple of minutes. So now